The formula for calculating the magnetic field strength at a transformer is the same as that for a single conductor. The formula is B equals 2 pi times A divided by R times mu0, where B is the magnetic field strength in teslas, I is the current in amperes, R is the distance from the source in meters, and mu0 is the permeability of free space, which is 4 pi times 10 to the power of negative 7 teslas meters per amp. To calculate the current I in the transformer, use the following formula: I equals P divided by V times the square root of 3, where P is the transformer power in watts and V is the line to neutral voltage in volts. For a three-phase transformer, the line voltage is different from the phase voltage. The line voltage, V, is given by V equals the square root of 3 times V phase, where V phase is the phase voltage in volts. Let's consider an example calculation. For a three-phase 480 volts to 120 volts divided by 208 volts, 15 kVA transformer, firstly calculate the line voltage. V equals the square root of 3 times 480 volts, which is approximately 831.5 volts. Secondly, calculate the phase voltage for the 120 volt side. V phase 120 volts equals 120 volts. Thirdly, calculate the current for the 120 volt side. I 120 volts equals 15,000 watts divided by 120 volts times the square root of 3, which is approximately 65.7 amps. Fourthly, calculate the magnetic field strength at a distance of 1 meter from the transformer. B 120 volts equals 2 pi times 65.7 amps divided by 1 meter times 4 pi times 10 to the power of negative 7 teslas meters per amp, which is approximately 8.21 times 10 to the power of negative 5 teslas. The magnetic field strength in the vicinity of a transformer decreases rapidly with distance as per the inverse cube law, 1 divided by r cubed. In summary, calculating the magnetic field strength of a transformer involves several steps. Firstly, understanding the fundamental formula B equals 2 pi times I divided by R times mu0 is crucial. This formula, applicable to both single conductors and transformers, relates the magnetic field strength to the current, distance from the source, and the permeability of free space. Secondly, determining the current I flowing through the transformer requires the formula I equals P divided by V times the square root of 3. This equation uses the transformer's power rating in watts, P, and the line to neutral voltage in volts, V, to find the current. For three-phase transformers, it's essential to differentiate between line voltage and phase voltage. The line voltage, V, is calculated as V equals the square root of 3 times V phase, where V phase represents the phase voltage. These voltage relationships are crucial for accurate current calculations. Let's revisit the example calculation for a three-phase 480 volts to 120 volts divided by 208 volts, 15 kVA transformer. The first step involves calculating the line voltage using V equals the square root of 3 times 480 volts, resulting in approximately 831.5 volts. Next, the phase voltage for the 120 volt side is simply V phase 120 volts equals 120 volts. Then, the current for the 120 volt side is computed using I 120 volts equals 15,000 watts divided by 120 volts times the square root of 3, giving approximately 65.7 amps. Finally, the magnetic field strength at a distance of 1 meter from the transformer is found using B 120 volts equals 2 pi times 65.7 amps divided by 1 meter times 4 pi times 10 to the power of negative 7 teslas meters per amp, which is approximately 8.21 times 10 to the power of negative 5 teslas. It's important to remember that the magnetic field strength around a transformer diminishes rapidly with distance, following the inverse cube law, 1 divided by r cubed. This means that even smaller increases in distance can significantly reduce the magnetic field strength. The permeability of free space, denoted as mu0, is a fundamental constant in electromagnetism. Its value is approximately 4 pi times 10 to the power of negative 7 teslas meters per amp. This constant is essential for converting current and distance into magnetic field strength. The units of measurement are critical in these calculations. Magnetic field strength is measured in Teslas, current in amperes, distance in meters, power in watts, and voltage in volts. Ensuring consistent units throughout the calculations is vital for obtaining accurate results. Transformers play a crucial role in electrical power systems, enabling the efficient transmission and distribution of electricity. Understanding the magnetic field strength around transformers is important for safety and electromagnetic compatibility considerations. The inverse cube law has significant implications for mitigating electromagnetic interference. By increasing the distance from the transformer, the magnetic field strength can be substantially reduced, minimizing potential interference with nearby electronic devices. In practical applications, various factors can influence the magnetic field strength around a transformer, including the load on the transformer, the design of the transformer, and the presence of shielding. These factors should be considered when assessing the electromagnetic environment around a transformer installation. Different types of transformers may exhibit varying magnetic field characteristics. For example, toroidal transformers tend to have lower external magnetic fields compared to EI core transformers due to their geometry and winding configuration. Shielding techniques, such as enclosing the transformer in a metallic enclosure, can effectively reduce the external magnetic field. The choice of shielding material and the design of the enclosure are important considerations for achieving optimal shielding performance. Magnetic field measurements can be performed using specialized instruments such as Gauss meters or Tesla meters. These instruments provide quantitative data on the magnetic field strength at specific locations. Regular monitoring of magnetic field levels around transformers can help ensure compliance with safety standards and identify potential issues. In addition to the fundamental formulas, computational tools and software can be used to model and simulate the magnetic field distribution around transformers. These tools can provide detailed insights into the magnetic field behavior and aid in optimizing transformer design and installation. Understanding the magnetic field strength of transformers is essential for electrical engineers, technicians, and anyone working with electrical power systems. By applying the principles and formulas discussed, one can effectively calculate and manage the magnetic fields associated with transformers, ensuring safety and electromagnetic compatibility. Let's delve deeper into the implications of the inverse cube law on magnetic field strength. The inverse cube law states that the magnetic field strength decreases proportionally to the cube of the distance from the source. This means that if you double the distance from the transformer, the magnetic field strength will decrease by a factor of 2 cubed, which is 8. Similarly, if you triple the distance, the magnetic field strength will decrease by a factor of 3 cubed, which is 27. This rapid decrease in magnetic field strength with distance underscores the importance of maintaining adequate separation between transformers and sensitive electronic equipment or occupied areas. In practical scenarios, the magnetic field around a transformer is not perfectly uniform. The field distribution can be influenced by factors such as the geometry of the transformer core, the arrangement of the windings, and the presence of nearby metallic objects. These factors can create localized variations in the magnetic field strength. To accurately assess the magnetic field environment, it is often necessary to perform measurements at multiple locations around the transformer. The measurements should be taken at different distances and orientations to capture the spatial variations in the magnetic field. When interpreting magnetic field measurements, it is important to consider the frequency of the magnetic field. In power systems, the magnetic field typically has a frequency of 60 Hz in North America and 50 Hz in Europe. The response of electronic equipment to magnetic fields can vary depending on the frequency. Some equipment may be more susceptible to magnetic interference at specific frequencies. In addition to shielding, other techniques can be used to mitigate magnetic fields around transformers. These techniques include using low permeability materials to redirect the magnetic field, optimizing the layout of the transformer installation to minimize exposure, and implementing active cancellation systems to counteract the magnetic field. Active cancellation systems use coils to generate a magnetic field that is equal in magnitude but opposite in direction to the field produced by the transformer. This effectively cancels out the magnetic field in the surrounding area. The design and implementation of active cancellation systems can be complex, but they can be highly effective in reducing magnetic field levels. When designing a transformer installation, it is important to consider the potential for induced currents in nearby metallic objects. The magnetic field from the transformer can induce circulating currents in metallic objects, which can lead to heating and energy losses. To minimize induced currents, metallic objects should be grounded and bonded together. The grounding and bonding should be done in accordance with applicable electrical codes and standards. In some cases, it may be necessary to use non-metallic materials for certain components of the installation to avoid induced currents. For example, non-metallic conduit can be used for electrical wiring to prevent the conduit from becoming a source of magnetic interference. The selection of appropriate materials and construction techniques is crucial for minimizing magnetic field effects in transformer installations. Regulatory standards and guidelines often specify limits on magnetic field exposure in various environments. These limits are designed to protect the public from potential health effects associated with exposure to magnetic fields. It is important to be aware of and comply with applicable regulatory requirements when designing and operating transformer installations. The International Commission on Non-Ionizing Radiation Protection (ICNIRP) publishes guidelines for limiting exposure to time-varying electric, magnetic, and electromagnetic fields. These guidelines provide recommendations for exposure limits at different frequencies. Many countries and regions have adopted ICNIRP guidelines or similar standards for regulating magnetic field exposure. In addition to regulatory requirements, best practices and industry standards can provide valuable guidance on managing magnetic fields around transformers. The Institute of Electrical and Electronics Engineers (IEE) publishes standards related to electromagnetic compatibility and magnetic field management. These standards can help engineers and technicians design and operate transformer installations in a way that minimizes magnetic field effects. Continuous monitoring of magnetic field levels and regular inspections of transformer installations can help identify and address potential issues before they become a problem. A proactive approach to magnetic field management can ensure the safety and reliability of electrical power systems. Let's now consider some specific examples of how the principles of magnetic field calculation and mitigation are applied in real-world scenarios. In data centers, where sensitive electronic equipment is densely packed, it is particularly important to minimize magnetic field interference. Transformers used in data centers are often located in shielded rooms or enclosures to reduce the magnetic field levels in the surrounding areas. Careful attention is paid to the grounding and bonding of equipment to prevent induced currents. In hospitals, where medical equipment is used for diagnosis and treatment, magnetic field interference can be a serious concern. Transformers used in hospitals are often designed with low leakage flux to minimize the external magnetic field. Shielding and active cancellation systems may be used to further reduce magnetic field levels in critical areas. In industrial facilities, where heavy machinery and equipment are used, transformers are often subjected to harsh environmental conditions. The design and installation of transformers in industrial facilities must take into account factors such as vibration, temperature, and humidity. Shielding and other mitigation techniques may be necessary to protect sensitive electronic equipment from magnetic field interference. In residential areas, transformers are typically located outdoors or in underground vaults. The magnetic field levels in residential areas are generally lower than in industrial or commercial settings. However, it is still important to maintain adequate separation between transformers and occupied areas to minimize potential exposure. Public awareness and education are important for addressing concerns about magnetic fields around transformers. Providing clear and accurate information about the sources, levels, and potential effects of magnetic fields can help alleviate public anxieties. Transparent communication and engagement with stakeholders can build trust and promote informed decision-making. The ongoing research and development in the field of electromagnetics are leading to new technologies and techniques for magnetic field management. Advances in materials science, computational modeling, and active cancellation systems are paving the way for more effective and efficient solutions for mitigating magnetic field effects. The future of magnetic field management will likely involve a combination of innovative technologies, improved standards and guidelines, and increased public awareness. By embracing a holistic and proactive approach, we can ensure the safe and reliable operation of electrical power systems while minimizing potential impacts on the environment and human health. Remember that the accurate calculation of magnetic field strength requires a thorough understanding of the transformer's parameters, including its power rating, voltage levels, and winding configuration. Furthermore, the surrounding environment and the presence of nearby metallic objects can influence the magnetic field distribution. Therefore, it is essential to consider all relevant factors when assessing the magnetic field environment around a transformer. It is also important to know that the formulas and techniques discussed here are applicable to steady-state conditions. In transient conditions, such as during switching operations or fault events, the magnetic field behavior can be more complex and may require more sophisticated analysis techniques. These techniques often involve the use of computer simulations and specialized software tools. In conclusion, the calculation and management of magnetic fields around transformers is a multifaceted topic that requires a combination of theoretical knowledge, practical experience, and adherence to established standards and guidelines. By applying the principles and techniques discussed, we can ensure the safe and reliable operation of electrical power systems while minimizing potential impacts on the environment and human health.